What's up, everybody? I'm Juan Pablo, leader of the new generation, and you're tuned into the new generation XTV. Subscribe to the channel and smash that like button. So, welcome to my lab, y'all. But before I show you exactly what's going on, I want to show you all these great prizes that my loyal subscribers will be eligible to win. So, make sure you watch the videos and get in on these prizes. Okay, so the new generation XTV, I have some prizes for y'all. So this right here that you're looking at in front of you right here, this is the Apple Studio display. Like, this is a big, pretty LCD that Apple has. The best visual quality you could get, you know. And that will be a prize for my subscribers, for one lucky subscriber, when I get to 300,000 subscribers. Actually, the mission is to get 300,000 subscribers within 3 months. And if I get to that goal, you guys will be getting this right here. And if we don't get it in 3 months, then it's going to be 6 months, right? So 300,000 subscribers by January, February, March. So that's our goal, to get 100,000 subscribers per month. And this will be one of your prizes right here. Right here, there we have an Apple laptop. This one, you know, is the MacBook Air. This is like the best laptop ever for personal use, you know. Like, it's like the thinnest laptop you could find. It's silent and you barely feel any heat coming off of it. You know? One of the best things I see out there. That will be one of your prizes as well. 300,000 subscribers by March of 2024. So now we're over here to the lab, right? So this is our electronics lab, and we're going to be building electronics from all these electronic stuff right here, right? This is it right here. So we're going to be making videos of that. And also, these will be included in the prizes as well. So you'll be able to win electronics prizes if that's what you're interested in, you know? So we're going to talk a little bit about the electronics that we actually have right here, you know? It's mainly basic components. It's basic components for these electronics right here. And we could start off with this box right here. So what we have in this box right here is a microcontroller, right? So that's like a little mini computer that you could program and use for embedded systems, use for embedded programming. So let's say like this thing right here needs to work. You need some kind of chip in it. It might be one like this. So as well as this TV right here. Whatever electronics device you use some kind of chip. And in this box, we have those chips, as well as sensors that go along with the chips, with the microchip. You know, let's look exactly at it. What it is it's not exactly an Arduino. It's an off-brand. So it's something like an Arduino. So you could program it and have it run your smart devices from this one. It could also be like the computer for drones, you know, little mini robots. Right here, these are MOSFETs. You're going to have to know what those are as electronics components. Let's open it up a little bit, give you a closer look. So this is a MOSFET right here. That's what a MOSFET looks like. And what it is a transistor. Well, that's another explanation of what that is. A high-powered transistor. That's what a MOSFET is. Right here we have a PWM, a pulse width modulator. We have some alligator clips for making our circuits. Right here is an AC capacitor. Over here we have a multimeter. We have the amp meter, voltmeter, also test frequencies, and all those will be prizes. So if you want to learn some electronics and build a few things, maybe maybe a sound amplifier, a speaker sound amplifier, or an inverter, or a voltage multiplier, these are the type of things that you would need for that. So we have some prizes for y'all. Make sure you subscribe to the channel, get the 300,000 subscribers, and be eligible to win this prize right here. So before we get back to the prizes, I'm going to tell you what exactly is our main focus for this lab. So in our electronics lab, with all our components, our main focus would be to try to make an over unity device. So this is an over unity lab. And if you don't know what over unity is, let's talk about unity. What unity is when you put a certain amount of electricity in a circuit, and the amount of electricity that you get back out is the exact same as what you put in. That is what unity is supposed to be. And technically, right now, that's not something we could reach. Let's just say it's impossible. However, I came across just a whole community of people on YouTube studying the issue years ago, and they've been working at it. So we're going to do a over unity lab as well. And like I said, before I get back to the sweet prizes, one thing we're missing for our lab is an oscilloscope. And what an oscilloscope does, that makes you able to visualize whatever electricity is going through the circuits, whatever circuit you're running. So it gives you a graph that shows you the voltage, the amperes, the time that it takes for all of it to happen, the type of wave that's going through the system, whether it's a sine wave or a square wave. Yeah, so it's an over unity lab. But back to the prizes. Check these sweet prizes out. Right here, we have the biker helmet for you. We got a nice bike helmet, whoever wants that helmet. Again, we see the big Apple viewing display, and right there the laptop. So we have some prizes for y'all. If y'all want to win these prizes, make sure you subscribe to the channel, watch all the videos, and leave a comment saying prize in the comment section. So right here, this prize right here, this is a sweet e-bike. Really nice e-bike. Foldable. Could throw it in your trunk if you need to go somewhere. Could take it to work, saving you on those Uber fees. So if you're trying to get in on this prize right here, subscribe to the channel, watch all my videos, and leave like in the comment section.
Long ago. Anyway, as Syed kindly mentioned, my name is Darren, co-founder of Unigrid Battery. We are a San Diego-based spin-off company from UC San Diego, and we're commercializing advanced sodium-ion batteries for clean energy storage. So this is going into the grid. For those who haven't heard of Inventor before, this is our story in a nutshell. Oh, my mouse is running around. Sodium is definitely the next big wave in battery technology, and we are moving very fast to seize this opportunity. Today, we've already made ourselves to be a clear leader in all of North America for sodium battery tech. We validated technology achievements. We hit 450 watt-hours per liter. We show on performance, safety. We do tests with third parties, validate them, and show that we are double that of the standards of Chinese and other competitors. Because of this, we managed to achieve significant traction and velocity. We are working with about 12 MTAs with different Tier 1 and Tier 2 EV and ESS makers. We have a number of JDAs in the pipeline, and we are working with megawatt-hour contracts that we have to deliver next year. So we may very well see our batteries in the first customer homes by the end of 2024. Today, we are rapidly scaling our US production and commercial operations. So why sodium? Sodium-ion battery seeks to address the challenges faced by lithium-ion today. Lithium-ion, we know, is expensive, it's unsafe, lots of supply chain constraints, especially in North America. Lithium-ion batteries use lithium, cobalt, nickel, all the nasty things associated with environmental concerns that we want to avoid. And none of these materials are available in the United States. If we look at the cost of lithium raw materials, you can see that the raw materials used to produce battery, which is carbonate and hydroxides, are about 200 times more expensive in lithium compared to sodium. And this is owing to the fact that sodium is way more abundant than lithium. If we look at this graph here, you can see the world's sodium reserves is about 3 orders of magnitude higher than lithium, and almost all of it is in the United States. So we joked about it earlier, we're putting too much sodium in our food and in our bodies, we should put more of it in our batteries. For these reasons, sodium-ion is fast becoming the next wave. There are numerous cell makers and OEMs starting to put sodium-ion batteries to power our cars, the grid, portable devices, and a variety of new emerging applications. So these are some news articles you see coming out from Asia and China. We see some EVs like the BYD Seagull can cost as much as little as $11,000 US. Something I would have loved to see as a grad student not too long ago. Although sodium-ion batteries do address this cost, the safety, and the material supply chain challenges of lithium-ion, their missing piece really is energy density. It's no secret that sodium comes with a 30% energy density penalty compared to lithium-ion battery. That really limits the drive range if you put it in electric vehicles, and increases the deployment footprint if you put it in a stationary storage device, which means your battery is going to be bigger. Customers don't like that, so we set out to solve this last piece. And by checking all these 4 boxes here, we can open numerous emerging market opportunities that conventional batteries cannot solve. The way we do this is through our key anode technology. So this diagram you see here in the middle is a schematic of what a sodium-ion battery looks like. It's made up of 2 electrodes. You got your carbon-based anode, and you have your sodium transition metal oxide cathode. Lithium-ion battery looks very much like this as well. What we do is we replace this carbon anode with a very dense tin alloy. This tin has about 3 times the capacity, about 5 times the density of carbon, so overall your battery is smaller and lighter. You can think of tin alloy anodes for sodium-ion batteries very much like silicon for lithium-ion batteries. They both serve to do very similar outcomes. How much does it increase by? It's best we look at this Ragon plot here. So this plot compares the gravimetric energy density, so watt-hours per kilogram, versus the volumetric energy density, which is watt-hours per liter. So there are 2 common ways to measure battery energy density. This dotted line here are where lithium NMC and lithium LFP are, the 2 most commonly used lithium-ion battery technologies. So lithium NMC is the most superior gravimetric and volumetric energy density chemistry out there, which is why it's used in the Tesla Model S, your Fords, your GMs, your Stellantis. Most of the electric vehicles used in America today is using lithium NMC. Lithium LFP is another lower cost solution that doesn't use cobalt or nickel. So NMC stands for nickel, manganese, and cobalt. That's what it means. And LFP stands for lithium, iron, and phosphate. So those are the elements that make up those lithium-ion battery chemistries. This blue circle shows where conventional sodium-ion is. You can see it is inferior to lithium-ion batteries both in weight and in space. So customers get upset, even though it is much cheaper than lithium-ion due to its abundance. What we do is solve this problem by doubling the volumetric energy density, exceeding that of lithium iron phosphate, So we achieve a balance of both sufficient energy density and low cost. This chart only shows a projection. Often we need to show that it's demonstrated and validated in the lab. So this is something we set out to do in the early days. We assembled a representative pouch battery cell that looks like this here. So this is the kind of battery you have in your iPhone. It's a very similar shape. It's rectangular in nature. It has about 20 layers of electrodes in there. Uses our proprietary tin anode and sodium cathode. And we show that the energy densities we can achieve here is significantly higher than your commercial LFP out there. So it's not just a projection, it's real. It can deliver what it promises to do. If we look at the entire battery competitive landscape, so we look at where we are compared to all other major sodium-ion developers here. Some of these names may be familiar to those in the audience. We show that we can leap ahead from them. So we look at who they are, where they're coming from, what kind of innovations they focus on, and what metrics are being reported. We see that most of the sodium teams come from Asia. China has really focused on sodium-ion batteries during the pandemic, but the US is far ahead in technology advancements. Right now, we are the only and the leaders in anode innovation. Most other teams are competing on the cathode, and that's where we stand out. We show we can double this volumetric energy densities achieved. And we can put ourselves on par with lithium LFP solutions. When we did this exercise, an interesting observation we made is that most of the cathode innovation teams, those you see in orange here, tend to come from Europe or Asia. That's because of a lot of historical reasons on the ceramic industries, the chemical producing industries. They all come from China, Korea, and Japan. And it was a small step for them to transit to produce battery cathodes. Whereas North America is famous for having anode material development. Most of them come from US university spin-offs like us. And many of them have developed lithium metal anodes, silicon anodes, anode-free lithium anodes, and all sorts of different versions that look like that. But the market dynamics are starting to shift. Instead of lithium-based innovations, the world is starting to shift to sodium. And today, we are the first to do it, but there are many others that will follow suit in the future. For sodium-ion batteries, the key value propositions lie really with cost, safety, volumetric energy density, and supply chain. So we look at the market segments, market gaps with the strongest competitive advantages for these four properties. And it's overwhelmingly clear that the US residential storage market is an obvious one. This is a market where upfront cost matters because people will want to pay as little as possible, they want to save as much money as possible. Payback times matter, they want their money back as soon as possible. And it's also one of the fastest growing markets in the United States, especially in California, where it is now mandated to have both storage and solar for every new commercial or residential building. The light e-mobility space is another one. This is where bill of material cost is quite big. In a Tesla Model S, your percentage of battery cost is about 20 to 30%. In a motorcycle, such as the picture you see there, the percentage of battery cost is 60 to 70%. It's hard to imagine like 60% of, two-thirds of your motorcycle is just the batteries itself. So lowering that bill of material cost by using sodium provides a strong incentive for many of these OEMs. Of course, finally, sodium's major application will be in the grid business. This is where levelized costs matter, and we want batteries to run for 20 years, 30 years if possible. These findings are very concisely summarized in this very large and menacing table. So this was compiled by the Volta Foundation. It's a battery report 2023. You can access it online. It looks at all the battery chemistries available commercially at the top, and all the different applications we look at: aerospace, automotive, consumer, grid, and military. Now, if we look at where sodium ion is and where it comes up green, it's quite clear that light vehicles, grid, as well as residential storage offer the most attractive markets for application. But the technology readiness is something we have to solve, and this was a key focus for us in the last 2 years. We really focus on advancing our technology readiness. We don't want to just stay in R&D stage, we want to get into market. 2021 was when we first spun out from UCSD. UC San Diego, and at that time we were working on prototypes that look like this, little button cells that you can buy in the supermarket. It was very good for demonstration, show it works, show the chemistry makes sense, but we needed to scale it to a decent size to demonstrate things like energy density. So not too long after that, we moved towards the pouch cells, the iPhone batteries that you see here. But this was great in demonstrating the metrics we report, but not so good for commercialization. Customers like something familiar. They like a standardized form factor. They like something with the simplest way for integration. And so we moved towards cylindrical batteries that you see here. This is about around double the size of a AA battery. We call this 18650. So for those who don't know, every battery has a couple of numbers you see on it. 18650 refers to 18 millimeters in diameter, 660 millimeters in height. If you buy a button cell, you see something like 2032, that means 20 millimeters in diameter, 3.2 millimeters in height. So all those numbers just refers to dimensions. Since then, we've started to do a lot of sampling. We ship a lot of these samples out to different customers, different OEMs. They collect feedback, send it back to us. We do third-party testing. And by early next year, we hope to get into pilot production, where we will start to produce megawatt hours of these units for delivery next year. So this is the first batch coming out from one of the contract manufacturing factories that come up. So it was a big milestone achieved. These are some pictures of our current lab facility. We are processing kilogram scale of materials, doing liter scale slurries. We are hand making all these batteries. So inside the cylindrical battery, you see a jelly roll, which is basically electrodes rolled out that looks like this here. With the rest of my time, I want to share some of the cell testing data. I was not briefed on the general nature of the audience here, so this can get quite technical. I'll try my best to explain what's going on. When in the battery community, we hear a lot of news about sodium ion coming from Asia, and some of them make crazy claims. Some of them say, oh, it's extremely high power, you can do this and that, all these fancy things. And that creates a lot of skepticism within the community, and that's something we want to prove, kind of like mythbusters, right? We go in and test it, say whether it's real or not. So we picked a couple of these data sets to show, to explain what's real and what's not. The first common claim is that sodium ion batteries deliver extremely high power and fast charge capabilities. To test this, we run several of the prototypes at various charge and discharge rates. So the graph you see here is voltage on the vertical axis, and you have capacity on the horizontal axis. And as you charge the battery, the voltage increases here, and when you discharge, the voltage decreases. So the faster you charge it, the less energy you can get out of it, which is why I always recommend you charge your phones with your USB cable, not the wall charger. The wall charger is terrible for your phone if you want it to last longer. And don't get the battery upgrades from Apple, get it from a third party.
That's the same for the sodium battery as well?
That's a different thing.
Okay.
Lithium has its own concept, and I have a long explanation on why that's the case.
Okay.
Yeah. I'm still using an iPhone 6, by the way. I take very good care of it. Yeah, it's an iPhone 6s. If you keep using it, you can be successful. Yeah. So here we run batteries at different, what we call C rates. So C rate is a general term used in the industry to measure how fast a battery is being run. 1C means you fully charge the battery in 1 hour. 2C means you fully charge the battery in half an hour. 4C means you fully charge the battery in 15 minutes. Right. So here we show that we can run up to 15 minutes charge and discharge, showing that the battery can handle a wide range of capabilities. And another common claim is low temperature performance. So it's not really a concern for us who live in California, but those in the East Coast have a big problem, even in the Midwest as well. Winter is coming. You're going to get a lot of grid problems, and people who even have batteries may not be able to use them well if the temperature is too low. For sodium ion batteries, when you have it running at negative 20 degrees Celsius, so this is, I'm not sure how much is it in Fahrenheit, but it's way below zero. You still can get more than 90% of its power and energy output. Okay. This is a marked difference compared to lithium ion. Lithium ion can probably get less than half of what you want to pull from it at this kinds of temperature. We have low temperature testing, we also have high temperature testing, so we run at 40 degrees, 55 degrees, and we're running it even higher right now. In lithium-ion batteries, you never want it to overheat past 40 degrees. Not only bad for the battery, it can be dangerous as well. But for sodium-ion, it's a lot more robust. So when you put sodium-ion battery under the sun, you can leave it, you don't have to run cooling lines across it, and customers really like that. Another interesting point about sodium-ion battery is its unique ability to withstand over-discharge. So in lithium-ion batteries, every battery you buy online or from the store come at a certain state of charge. That is, they have certain charge in it. That may sound good, but it's actually really dangerous because when you have millions and millions of cells in the warehouse, or when you park a car in the garage over a long period of time, there's always a chance that it's going to catch on fire. Likewise, you also don't want to leave your if you're not using your laptop, not using your phone for too long, you want to charge it occasionally because once it reaches 0% or below, it starts to do a lot of damage to your batteries and you likely cannot use it to its fullest extent again. But in sodium-ion batteries, you don't have this problem. We can store and transport it at 0 volts, so it's a lot safer. This is a lot better for the workers and the technicians who are also assembling packs that can go in extremely high voltage. So when everything's at 0 volt, it limits the risk of electrical shocks and fire safety. Moving on to safety testing, we engaged a third party to do a bunch of safety tests set by the UL guidelines. The first of which is thermal abuse. So what we do is we fully charge the battery and we heat it up to 130 degrees Celsius. Basically, you try to barbecue the battery. When the battery is heat up, you see the temperature goes up and stays at about 130 degrees. And when there's no fire or explosion, we call it a pass. Please don't do this for lithium-ion cell. Likewise, we also short circuit the battery. We short circuit it at room temperature and at 60 degrees at a fully charged state. Monitor the temperature, it goes up a little bit to about 80 Celsius or so. Sorry, 70 Celsius or so, but no nasty things occur. We also overcharge the battery. So overcharge is one of the common failures for lithium-ion. In sodium-ion, we overcharge it to 5 volts, hold it at 5 volts for 1 hour. Nothing nasty happens. We call it pass. We also crush the battery, so we use a hydraulic press like those you see on YouTube. It presses it into like kind of a potato shape. No nasty things occur. We also do a nail penetration, so this simulates something mechanically destroying the cell. We have a couple of videos from there as well. So let me interpret what's happening here. The top left-hand corner, we have a lithium-ion battery that's being penetrated, and you see it burst into flames. The temperature rises to about 600 to 800 degrees Celsius. So when you have a lot of this together in either a car or in your home, people feel very uncomfortable with that. And on the top right-hand corner is a sodium-ion battery cell that is you buy from China that uses a conventional chemistry very similar to lithium-ion. It doesn't really burst into flame like lithium-ion, but it still releases a lot of heat, a lot of smoke, may induce other things to catch on fire. The one at the bottom is sodium-ion produced by us. It's really benign. Nothing really nasty happens to it. You see some bubbling of the electrolyte leaking, but overall it's very mild. Maybe I should skip this. I can explain it in another way. So the reason why our technology is a lot safer is due to the intrinsic properties of the material we use. Because we use a tin anode. Tin is a metal. Right? A metal doesn't burn. Metal is not fuel. When we heat tin up, it melts, eventually oxidizes. But carbon, which is the conventional anode material, is a fuel you can burn. That's why we use it for barbecue. So it releases a lot more heat when things go up, and that's how thermal runaway occurs. So for the same amount of capacity stored, carbon releases more than 10 times the amount of energy compared to tin. That's why we're seeing the huge safety improvements when we switch to our materials.
It's your own 11 times.
This is my last slide. So all these successful safety tests and performance tests have provided our partners confidence and assurance that when they receive our cells, they'll be safe, they can test them and evaluate them without triggering the fire marshals to come. So we are constantly looking for new partnerships and collaborative opportunities. If you know anyone, any team out there interested to explore sodium, either to halve your cost, offer a superior safety metric, or extreme temperature operation, we're happy to help. I'm happy to take any questions and have an open discussion.
Good job. It's safe. That's one thing. I noticed that, right? From lithium ion, yeah, there's a lot of fires and stuff. From if the circuit, if let's say you're in an accident with a car, right? If the battery breaks, that's a fire right there. And you're saying with the sodium ion battery, with the tin anode, that doesn't take place?
So for cars, you have a different safety standard. People don't blink an eye when the garage catches on fire, but people get really upset when their home catches on fire. So when we start putting batteries in homes, in apartments, in offices, the safety standards are raised way above. So we're not talking about reduced chance, we're talking about zero chance. So that is the promise that we have to make to the OEMs. The OEMs to make that promise. People like Sunrun and SunPower have to guarantee that for their customers. Because now we're dealing with people's livelihoods, people's homes. It's really different from them losing a car and having insurance tow it away.
There's a question on this, Daniel.
Yes.
Can you, I can't tell for the mic. Who you speak to the mic?
I can't see the question.
He's going to ask it, I think. You ask Daniel on the line.
Oh, hi, Daniel. Can you speak into the...
Sure. Can you hear me now?
Yes.
Great. Excellent presentation. Very interesting. On slide around 22 or 23, you were talking about the cycles tested after a complete discharge. They only seem to go to like 70 cycles. Was there something missing on it? Did you try 700 cycles after a full discharge?
Right, yeah. So let me jump to my cycle. I skipped that because it requires a little bit more explanation. So we started cycle life testing a couple months ago. We ran a half C and 1 C, which means each cycle is 2 hours or 1 hour. We've hit about, now today the latest data is about 600-700 cycles so far. The industry standard for a home battery is about 2,000 to 3,000 cycles. That takes about a year and a half of testing. So we need more time to get there. Currently, the benchmark we use is the electric vehicle benchmark, which is the highest benchmark to reach, which is what the cell state of health would be. How many cycles does a cell need to reach an 80% state of health? Because 80% of its original capacity is when the industry regards the cell reaching its end of life. With our current projection, we should cross the 1,000 cycle mark comfortably. We are aiming for 2,000 and 3,000 in the future. Hope that answers the question.
Well, actually, it was a slide after the 0 volts. In other words, if there's an unintentional complete depletion, lithium gets very damaged if you go to 0 volts.
Correct.
And I was very happy to see that you're very resistant to damage at 0 volts. It's just that there wasn't really a large cycle test after that, and that's where the damage shows up on the lithium, is that the lifetime of the battery is greatly reduced if you bring it down to 0 at any time in its life.
Yes, I agree. We do have longer ones for this. It's just my engineer didn't plot enough cycles for this.
No problem.
Yeah, the fundamental reason why that is the case is because in a lithium-ion battery, you use copper current collectors on the anode, and copper is really bad for low voltage problems because copper dissolves in your electrolyte solution and it starts poisoning your electrodes. But in sodium-ion battery, you use aluminum on both sides of the current collector. So you don't have any of these problems. So you can, go over discharge it whenever you like, and it's not going to do anything bad to yourself.
Just a second question then on the pricing. I was very intrigued, certainly with lithium prices several times what they have been historically, that you could still have a very competitive advantage. But the biggest problem with all sorts of chemistries is that people find that, yes, they can hand make these batteries, and they can even do slow rate production. But to get to billions of batteries turns into an impossible task. Even for Tesla, they've been trying to work on their battery mass manufacture. What do you see as the biggest hurdles to manufacturing of your battery?
That's an excellent question, and that is actually the most common pitfall for any battery startup company in the last decade. Any battery startup in the last 10 years, no matter how good the technology, they are stuck at the scaling side. They cannot manufacture it either in the quantities they want or at the cost they want. And that is the path we want to avoid. We don't want to, brute force it. The mistakes previous companies try to do is they try to raise as much money as they can from every venture capitalist they can pull in, pour as much money as they can into gigafactories in mountain states in the Midwest, and they still cannot succeed, which is why 99% of lithium-ion batteries in the United States is still imported from overseas. So instead, what we choose to do is design our battery to be directly compatible with existing lithium-ion manufacturing lines. And we go to them, we go to Korea, go to Japan, go to China, and say, hey, are you interested to produce our technology for us? And they say, oh, hey, we have 30% underutilized lines in our current gigafactory because the economy is slow. Sure, we can take your technology. And we engage them, we use their machinery, we use their labor force to produce it for us, and we buy from them at the cost they produce there. We've done it. We have about 3 contract manufacturers so far. We're engaging a 4th very soon. The quality is really good, the costs are extremely competitive, and we believe that's the way to go.
Thanks. It's makes a lot of sense, and it's a good idea. I'm concerned with the intellectual property. You seem to be very straightforward in its design and understanding of the technology. How do you anticipate controlling patents? Are there any involved? I don't know how you can control that somebody's not going to, Panasonic might come out with a salt and pepper battery. I don't know.
Yeah, that's a common question that came out. And it's really one of our first concerns when we work with contract manufacturers, especially those in China, which have been notorious for openly infringing on US IP. So we have 5 IP filings in the portfolio. We have 6 by the end of this year. These cover our anode materials and our electrolyte materials. Now, in your battery manufacturing process, you start with materials.
That guy got somebody on the phone.
You print the ink, you dry it, you cut it, you roll it, you wind it up, and you finally put your electrolyte in and you seal it. So if you notice, the IP-sensitive portions of our battery are at the start and at the end, which is on materials and the electrolyte. That's where we file our IP on. That's what we will keep here. So when we work with contract manufacturers, we pre-mix all the materials, so we don't have to disclose what's in there. We ship the pre-mix to them. They will do the middle portion, which is the capex-intensive, labor-intensive, really tedious parts. They ship the pre-completed versions back to us. We do the final integration. This way, we don't have to disclose what our electrolyte is. So that's how we balance out the IP portion. I think another portion that is a gap is, if we do this way, how do we benefit more from the IRA subsidies, Inflation Reduction Act? That's still an open question. The greater percentage of manufacturing that we do within the United States, the more subsidies and tax incentives we will get. So that's something in the long term that we have to consider beyond IP.
Thank you. Excellent answers. I do have one more question. I was noticing on your voltage that lithium has a plateau for, I guess, the characteristic voltage of that particular chemistry, where it spends most of its life under load, whereas yours is more traditional, like the carbon. Am I misunderstanding that, or is that sort of a fair assessment?
That really depends on which lithium-ion chemistry you're talking about. I think what you're referring to is lithium LFP, where it has a generally flat voltage. NFC
Yes.
looks very much like this.
Interesting. Okay, because I just assumed that there was a plateau between the end of charge voltage, and it goes rapidly down for a couple of millivolts, several millivolts, and then stays at 3.7, for example, the lithium ion does, and it stays at 3.7 till about 80% or 90% of its consumption.